Vamsee planned to give the talk to Zoom. That's why he's locked in. I can see.
Hello.
Yes. Thank you, Mahima. Thank you. So the two token biologists, are there any new students in biology? Any new graduate student from biology department? Yes? No? Okay. Please spread the word. Not for the colloquium, but also for the pastry. Yeah. I can see our colleagues and yeah, the chemists. Where are the chemists? Oh, that's right here. Other traveling or something? Victor is outside. Victor is all. The other people will come. Are you a new student too? Okay, welcome. Nice to see a full hall. Great.
Okay, so we'll actually start today on time. I'm just waiting for 2 minutes. So, it's actually just for everybody's sake. I would like to welcome all the fresh graduate students who have just joined TIFR. A warm welcome. And I know this is a process which is pretty intense to get into TIFR. So congratulations to all of you. A big round of applause for yourself, please. And thank you for coming in to probably your first NSF colloquium. And for some strange reason, you are the very first batch to receive pastries as we enter the colloquium. So it just turned out to be the right day. Okay. Before we actually introduce our colloquium speaker today, I would like to sort of just briefly give you a history of the NSF colloquium. For those joining for the first time, the NSF colloquium is an idea of putting the physicists, chemists, and biologists, as we call them at TIFR, as natural science faculty members, together under one lecture theater for at least an hour, so that they can listen to a very broad colloquium-based style talk from an expert, eminent expert in any of the natural sciences fields. Okay. And this was an idea that developed because of our founding director, Professor Homi Bhabha, who used to visit TIFR on a Wednesday due to his busy schedule, and he would meet all the faculty members in the institute and listen to this colloquium. And the genesis of the idea was because of Bhabha's schedule, but it turned out to be a very successful one because of this one single talk that everybody would hear. There would be discussions interdisciplinary, which is very important in any scientific attribute of a scholar to understand science through the lens of the physicist, chemist, and biologist. And it's sometimes as we age, we forget that. Some of us faculty members forget that, but it's important that this is cultivated at a very early stage. So this colloquium has for years now tried to cultivate that habit of listening to a biologist if you're a physicist, or listening to a physicist if you're a biologist or a chemist. Okay. So that is going to be sort of one of the things that is unique about this institute. And I'm happy that all of you will experience that. This is a blessing. So today's speaker is actually Vamsee Voora, Dr. Vamsee Voora. So he has been in the Department of Chemical Sciences for almost 4.5 years now. And he is a young colleague of mine. I'm in the Department of Chemical Sciences as well. So Vamsee actually is a theoretical chemist. And by the title of it, I think he should connect to everyone in this audience. As you can see, understanding nature's squishiest and tightest one-particle states. He will talk about what those are. But just to give a brief background of Vamsee, Vamsee did his bachelor's with honors in chemistry from Sri Satya Sai Institute in India. And then he went to University of Hyderabad where he did his master's in chemistry. And during this time, he worked with Professor Sushanta Mahapatra, which sort of probably led to him to be connected to theoretical chemistry ever since. Then Vamsee went to do a PhD in theoretical chemistry with Ken Jordan in University of Pittsburgh. And that's where his sort of all theoretical methodology development training started from. He then went for a postdoc with Philippe Fouché at University of California, Irvine. And in 2018, December, he joined us. So Vamsee has strong interests in looking at weakly interacting systems, electron molecule binding energies, looking at electronic states of anions, which is something of his very close to his heart, and also defects in large extended systems. So Vamsee, without further ado, I welcome you to give the colloquium.
Yeah, thank you very much, JD, and I hope you can hear me well. So, yeah, it's a great honor to be speaking at this colloquium, and it's nice to see a very packed place. So, in this particular talk, I'll be discussing one-particle states. What are these one-particle states? I'll be discussing them in detail. We'll try to understand where they're relevant and what is the physics behind such one-particle states. So, yeah, so just to start things off, right? So I just wanted to first, just for the audience sake, tell you what is theoretical chemistry, right? So basically, we are just trying to understand molecules, and these molecules also follow certain laws. So this could vary from very simple aspects, like very simple theories like the Newtonian mechanics. So when you are thinking about large biomolecules like proteins, the way they move, the way they wiggle and jiggle, there you have to think about Newtonian dynamics. But the moment you go to smaller systems where you're thinking about electrons or protons, at that particular level, you have to use a different type of equation of motion. Here you have to use Schrodinger mechanics. And in addition to that, suppose you have systems where particles are moving very fast. We'll try to cover some parts of it where particles are moving very fast, approaching some fraction of speed of light. You have to start thinking about using Dirac equation to understand energetics and dynamics. So basically, theoretical chemistry entails using different theories from physics and also, concepts of statistical mechanics and thermodynamics to understand chemical problems. Now, broadly speaking, what do I do, right? So while all theories are well defined and what we would like to reach is chemical understanding, there is a huge gap, right? So while theories are there, you have to solve equations, which involves certain computational complexity. And what I do is develop algorithms and approximations. So we have exact theories, but to tackle a certain chemical problem, we have to make specific tailored approximations. And those approximations have to be also designed such that they can talk to computers. And in such a way, we can solve chemical problems and develop chemical understanding. So approximations that I'll be talking about today include wave function methods and also density function methods. And in this context, I just want to name John Pople here, who was a Nobel laureate in '98. The reason he got a Nobel Prize was not for developing some, fancy theories, but because he developed computational tools which really revolutionized how chemical problems can be addressed. Okay, so this was John Pople in '98. And specifically speaking, what do I do? So I look at the intersection of many body problems and chemistry. So where do they occur? They occur in many places. Just to list a few that I'm interested in things like electron molecule interactions, where you have to think about many body dispersion effects and many body polarization effects. You could also look at X-ray spectroscopy, and here I'll discuss how many body polarization effects are important. And if you think about van der Waals interactions, that is another area of interest for us. Here you have to think about many body correlation or dispersion effects. Now, what are the challenges in general? Yeah.
Go back to the previous.
Yeah.
If you go back, right. So when you talk about, four. When you talk about electron molecule interactions,
right,
what kind of energies, kinetic energies for the electron are you interested in? I'm assuming you think
It's-
about it in terms of a reference frame fixed where the molecule is at rest.
Yes. So always I'll be talking about neutral molecules and there's an electron coming in. So these electrons could have an energy of few eV in the positive side. And then, also on the negative side, we'll be talking about something like few MeVs all the way to kilo EVs. Okay.
No, that's not the electron, right?
Yeah.
The electron is coming from outside, so it has a positive energy.
Yeah, if it is an electron coming from outside, it has a positive energy. I'll also be taking an electron out.
Sure, absolutely. But then if you're taking an electron out, are you putting in a photon or are you putting in an electron?
Yes, we're putting in a photon.
High energy photon.
Yeah. So these photons, the energy of these electrons, which are bound to the molecule, could vary from few MeV all the way to kilo EVs. Okay. Yeah, so I think I won't be talking too much about scattering. I just show one particular slide. So where an electron is coming in with a positive energy. So I will be, so the challenges that we face in these problems are usually the scale problems, that is the computational scaling. And along with it, as you try to study larger and larger systems, you have to make approximations. And when you invoke approximations, you start to, face the wrath of accuracy. So you have to start making reasonable approximations. At the end of the day, we also don't want to be just number crunchers. We would like to understand how why the numbers are the way they are. So these are the challenges we would be facing. And just most of the talk today will be focusing on the weak electron molecule interactions. And that part I'm going to call it as a squishy, and the other part that I'm going to call as tight, where we'll be talking about electrons which are bound very strongly to the molecular systems. Now, let us start with.
Are you setting an energy scale for squishy versus the two sides? How tight is the binding?
Yeah, I would say anything below 5 eV are squishy to my knowledge.
Okay.
Right. And anything above 5 EV.
It's just an operational thing, or
No, it's more to do with
something internal you will compare with? Saying
there is no simple definition here. Okay, so this is something I have just put it on the fly. But what you can do is think about polarizability, right? So if you think about polarizability difference between the ionized state versus the neutral state, the difference per electron, that is going to be huge in certain squishy systems that I'm going to talk about. Okay.
are you going to talk simple molecules or big chains and stuff?
So we will go from molecules to a few chains, not large chains.
Yeah.
It's let me ask this question in a different way. I mean, when you say 5 EV or so,
yeah,
I'm not able to compute right off the cuff, but what is the corresponding Compton wavelength? Let's say an electron, 5 EV electron we are talking about.
Right.
Okay, so the Compton wavelength, so 1 MeV, 200 MeV is per meter. How much is 5 EV? 5 EV is like 10 to the 10, about 10 to the 6 times that much. 10 to the 6 for me is.
See, you're talking about the localization of the functions.
Yeah. So sorry. Yeah. Nanometers. So you're talking about nanometers, right?
I would say these are sub-nanometers, I think.
Fraction of a nanometer.
Fraction of a
So
nanometer, right?
nanometer, I see. So they're basically wavelength of light. Smaller. So okay. So to connect to Ravi's question, I'm asking whether you can resolve the difference between an atom and a simple molecule, small molecule, with that length scale.
Length scale of the electron energy. That's what it is.
Sorry, I'm still not getting it. So can I resolve the energy?
See, if you have nanometer scale resolution, spatial resolution,
Right.
okay, then you can put fairly big molecules in there, okay, and they'll look the same to the
Yes.
electron as a single atom.
Waves. There will be localized waves which would be spanning several molecules. There will be some which will be just localized on an atom. That's where the tightest.
Basically, the electron wouldn't go.
It won't know the difference. Yes. So I'll show images which will help you understand this. So just to set things up, right? Let us start by definitions, right? So what I call as one particle energies are basically energy differences between the n particle wave functions energy minus the energy of the n-1 electron system, where here I will always be using as reference the neutral system in the ground state, and the ionized system could be in any of the excited states. Okay, so these will be called one particle energies, okay, which can be computed very well. We could have ionization potentials corresponding to these one particle energies. So in fact, IPs are defined as negative of these negative of these energies. And you could also have electron affinities, that is energy required to add an electron to a neutral system. So here you have an energy of psi 0n, where n particle system is in the ground state. And then you can have an n+1 electron system, which could be in any of the excited states. So these are my definitions of one particle energies, essentially energy needed to add or remove an electron. Now, how do we measure this, right? So what is the experimental relevance? So the way to measure it would be that you shine either a UV or X-ray onto the molecule, and then it goes into an excited state where you go into the n-1 particle state, and an electron is also ionized simultaneously into the continuum. And what you measure, the observable here, would be a binding energy, that is the traditional name given to this, which would be the energy difference between your input photon energy minus the photoelectron that has been emitted. So that is the measurable quantity that you would be using for. Now, how do we determine this theoretically, right? So one way to determine that would be, so here I'm going to condense all the theory to few slides. So sorry about the rigor at this point. So one thing you can do is go about determining the energy using wave functions. So as I said, you need one particle energy, which are differences between two energies, total energies. These energies could be computed using a variation principle. So suppose you start with a wave functional, so energy as a function of wave function. You could minimize this particular functional, and then you can find out the ground state. Now, practically speaking, you can't do this for more than two body systems. It becomes very hard. So what you do, you make approximations. One of the simplest approximations you can make is to assume that this wave function is made up of a single slated determinant that gives rise to what is called as a Hartree-Fock theory, which is something which I think some of us learned, right? Yeah.
So the binding energy equation, do you have an equivalent for the walk function in the molecules or no?
We have.
So in metals, you know that we have a Fermi level and the vacuum levels are different.
We have an equivalent of the lowest ionization energy,
okay,
right? Or we have the highest electron affinity. So we have these two equivalent, but work function would be slightly different, I guess. So both are measurable through same experiment.
Mm-hmm.
Okay.
So in that equation, the binding energy is like h nu minus kinetic energy.
Yes. Right.
So there is no term that comes in which would be equivalent for the walk function for the molecules or something.
I guess the point at which, h nu equals kinetic energy, that could be like a work function, I guess.
Because, I mean, these are all very coarse states that you're talking about.
No, not just coarse state. It could be valence as well, right? So when you do a photoelectron experiment, you get multiple peaks.
Yeah, that's fine.
Right.
Okay. So, I mean, basically, so there is no, your vacuum level is basically what there's no concept of
the vacuum would be continuum. So the continuum for ionization, right? That would be the vacuum level, right?
Okay.
Yeah.
So going back to my little chemistry, are you going to talk about HOMO, LUMO, all this?
Yes.
So you're going to talk about orbital structures, which are, so when you say your psi or whatever that represents linear combination of.
So these size are many body wave functions.
Okay.
So I'll go to one particle picture in a little bit.
Okay.
Yeah. So these are all many body wave functions at this point. We will just go to a simple picture where you have just one particle wave functions.
Okay.
Yeah.
So, but then there is no, so there is no like cutoff in this equation. So you will get basically even at very small h nu, you would get some electrons out. Is that
No, right? Only starting at the ionization potential.
Okay,
right?
so
Yeah.
So
maybe-
correct.
yeah, but
Is that orange? Yeah. Yeah. So I was just talking about
So this my idea about this, because I don't know about it, that affinity, right?
right electron affinity.
Electron affinity. So I can imagine a situation in which the electron is captured into a highly excited state above whatever is already there, above the core, and then decays. But the electron affinity is whatever is the lowest state that it can decay into minus the core. Is that right?
Yeah, I think that is one way of saying there could be multiple electron affinity states. So that will be something I'll talk about. Now there could be states going ahead. I get there could be states where you can auto-ionize. So which is what I guess Vaibhav Prabhudev is not here, he does. But there'll be states which are stable. They have infinite lifetimes. Okay.
Auto-ionize is when you have a bound state in that.
Yes, when you have bound state in the continuum that can auto-ionize. So we will not talk too much about it. Yeah. So the other way of determining energy functionals is through density. Okay. And this is the famous density functional theory. So where essentially I have condensed all DFT into one slide here. So you have what Hohenberg and Kohn in 1964 showed was that there's an exact mapping between many body wave functions and the density. Okay. So knowing the ground state density, you can determine the nuclear framework, and from the nuclear framework, you can actually determine the wave function. Okay. So what this is essentially saying is that now instead of working with wave functions, you can work with density and you can also use a variational principle, keep varying the densities until you reach the ground states. Okay. So that is the concept of density functional theory. While this is just a concept, you have to make practical approximations. And one of the practical approximations is a Kohn-Sham flavor of density functional theory. In Kohn-Sham flavor of density functional theory, what you do is you express the energy functional as a function of 4 pieces, where you have this kinetic energy part, Hartree part, which is classical electron-electron repulsion. And then you have exchange correlation, which is an unknown piece, which is approximated again. And then you have the nuclear electron portion. Okay. And in Kohn-Sham flavor of density functional theory, there is one more mapping which is done where they say that the interacting density, right, the density of the interacting system can be mapped to a non-interacting system. Okay. So if it is non-interacting, the density could be written as summation over occupation numbers. These are occupation numbers NP times the orbital squares for a non-interacting system. So you have 2 mappings. One is between interacting systems, wave function and the densities, and then there is non-interacting system and its density. Okay. So now you can write, and now one of the major advantages of doing a Kohn-Sham flavor of density functional theory is that you can compute kinetic energy portion almost exactly. So this really revolutionized the use of density functional theory in chemistry. You can make several approximations to this unknown functional. A common approximation is again Hartree-Fock form for this particular functional. You could also make other approximations like semi-local approximations and so on. There's one more approximation which is called random phase approximation. Okay, so what I'll be talking about in this particular talk would be these 2 approximations, Hartree-Fock and RPA, random phase approximation. I won't give you details about why the name RPA comes about, but I'll tell you what is the physics involved in RPA method, right? So once you express density as this summation, there is an advantage. Now, I'll just come to that in a little bit. As I discussed before, yeah. Yes, sure.
So if you were not to make the Kohn-Sham approximation,
right,
what would break down in this?
Nothing. I mean, okay. So if you don't make a Kohn-Sham approximation, this is still valid, right? But designing functions becomes much more harder. So one of the harder parts is actually designing kinetic energy functions. So kinetic energy is highly non-local piece. And if you want to design it through just using the information of density, it turns out to be a very hard problem. So if you were to somehow figure out kinetic energy functionals T as just a function of density, right? That's a very hard problem. If you can design that, then you can still use this particular equation without using a Kohn-Sham framework. The Kohn-Sham framework and the original flavor of DFT, the only difference is that in Kohn-Sham flavor, you are approximating the kinetic energy using this non-interacting system.
I see. So if you were to design some other kinetic energy,
Right.
that would of course change the EH, and
Right.
all the other
Accordingly,
energy.
other pieces would change.
Yeah.
Yes.
Okay.
So if you can do that, and it's actually, there is a whole group of chemists who are working on this particular problem where they're trying to design kinetic energy functionals. Right. So as I was saying, now this particular framework has an advantage, right? So you can compute one particle energies through this difference. The other thing you can do is you can now use a derivative approach. So what you can do is you can try to take derivatives of this energy functional with respect to occupation numbers. And this gives rise to what are called as one particle energies. Okay. So once you do this derivatives, you get this one particle energies, which we as chemists call them as orbitals. And this can be thought of as an expectation value of this one particle states, orbitals. And then you have these 5 pieces to your Hamiltonian. So now instead of having a many body Hamiltonian, you have a one body Hamiltonian made up of all these terms. And then you have, instead of having many body wave functions, you have one particle wave functions. Okay. So this is basically setting up the stage for all the theory that I'm going to use. So what we would do is we are going to look at, again, simple approximations to this one particle Hamiltonian. So you could have these first 4 terms. You have the kinetic energy, the Hartree nuclear electron and exchange portion, which is commonly called as the Hartree-Fock portion. And then you have this correlation portion where I would be using random phase approximation. Okay. So just to think about it, so what does this include, right? What are these terms? So kinetic energy, the term we know. Then there is a Hartree potential. Essentially, it tells you what is the repulsion felt by an electron which is in orbital phi I. And VNE would be the nuclear electron attraction for an electron in orbital. Yeah.
These 2 terms are dangerous. One is this exchange correlation and the polarization term in many electron systems,
Right.
as we suffer in atomic physics also. So these many polarization term and the exchange interactions. Are you? That's my question. So are you using those explicitly in the, because many times I have seen people use some empirical formulas and all these based on what molecular they're using, but that is even more than 20 years.
Right.
Now, in this, are you going to use those as a ab initio way?
Yes, yes.
Something?
So I'll be actually splitting this VC into a polarization term and a dynamical correlation term. So I'll be splitting that actually. So thank you for, preempting that. So anyway, so I'll be doing that in a little bit. Okay. So, and what is this exchange piece? Exchange piece is if you have an electron in orbital I, what kind of Fermi exchange you would feel from other electrons. Okay. And this correlation piece is an interesting one that I'll talk about. Now, before going ahead, right? So, so now having set up this stage where you can do derivatives and you figure out one particle energies. Yeah.
Justify that some parameter would need to be small or something for these to be well justified approximations. Is there a control parameter which tells you when this is good or when you need to add RPA, or you just do it and see and how much it matches with experiments? That's of course the other way of doing the calculation. You just do and see whether it matches with experiments.
No,
like, do I have a sense of when I can get away with doing a Hartree-Fock calculation and when do I have to include polarization?
Very
RPA?
thumb rule type answer, right? So when you're looking at valence neutral systems, right, there Hartree-Fock is very good because of cancellation of errors. And this is commonly called as Koopman's theorem, right? And on the other hand, once you go to anions, especially, right, the Hartree-Fock theorem fails because these two effects tend to add up and it doesn't work anymore. Okay, so I'll be talking about cases where Hartree-Fock gives you 0 bind. So maybe that will help you. So there is no longer a good, 0th order approximation, right?
And we're going to get deeper into the theory now. But before that, I just wanted to get a feel of exactly what kind of questions are you trying to answer?
Yeah, so I will be talking about what are the different types of many body effects that contribute to.
That's theory. What kind of, what is the answer that you want to give to somebody in the lab? What kind of questions can you ask?
Yeah. So see, okay, this one particle theories, right? They actually form the basis of a lot of chemistry, right? So whenever people talk about chemical reactivity, they talk about matching between the highest occupied orbital and the lowest unoccupied orbital of two chemical reactants. If they match, there's a chemical reaction, there is an electron transfer. So I can help you understand such chemical reactivity in.
You want to say things about. So I'm just trying to understand whether you want to say things about two molecules interacting, or probably two ions interacting, or you want to talk about an electron and an ion, or an electron or a molecule interacting. What kind of question are you specifically asking?
So at the moment, I'm only talking about how electrons interact with
Electron and ion. So some ionic core and an
electron, right?
And what is the precise property that you'll try to, 1 or 2 or 10 kinds of properties that you want to predict of this?
So the properties would be, maybe I'm repeating. So this is, the properties would be just the ionization potentials, right? So those would be the properties.
But then, since we discussed that at these electron energies, the quantum wavelength is so large that it doesn't see whether you're talking about an ion, an atom, or a large molecule. Okay, why are you doing it this way?
But see, we are not just restricted to understanding things at atomic levels, right? We would also like to understand molecular properties.
Yes, I understand.
Right.
But the electron doesn't know whether you're talking about an atom or a molecule, or the large molecule. Okay. So why would you want to go into a computational scheme, okay, where a large molecule, a very large molecule, you cannot. We just discussed that the size of the quantum wavelength is nanometers.
Right.
A nanometer length molecule is pretty large.
Right. But suppose you were to bring two such molecules together, right? They may still have interference between them. So you would like to know the individual molecular properties to understand assemblies, right?
So I think some of this question was, you said explicitly that it will be the electron meeting a molecule. And the next time you said it will be two molecules, whether the reaction takes place between them or not. I think that's where the confusion was. So if it's the former problem of just an electron seeing a big cloud,
right,
then it seemed like the entire thing is a cloud, no matter what the internal structure is.
Yes. So
if it's two molecules, then of course you talk about, this level matches that level, or reaction happens or not.
Right.
So maybe just some clarification, Mike.
So I'm
I think
electron in a molecule approaching another molecule. Is that what you're talking?
Yes, I mean, you could think about reactivity between two molecules, right? And that can be sometimes summarized in just the way in which the levels match, right? So that's where this information about
that reactivity.
Right.
So in other words, you define two quantities: ionization and electron. Ionization.
Electron affinity.
How large are those?
So those would be going from milli-electron volts all the way up to thousands of electron volts, right?
Okay, but again, if we come to 5 electron volts and smaller, milli-electron volts are even longer than almost.
Yes, absolutely.
So how does this electron even know what molecule it is? Only through its energy. Right?
No, I'm trying to ask the counter question. What is wrong with that, right? So now you have.
It just becomes complicated. Unnecessarily.
But
you want the simplest possible.
No, but this means there are new possible states which encompass the whole assembly of molecules, which could also be interesting, right? So one of the interesting aspects I'll be talking about is nearly free electron bands. So when you have such,
so if I have a large, It's conformational changes to change energies. Okay.
Right.
Now, very big conformational changes. Okay. Are different from small changes in some little subunit. Okay. Now, thing with the quantum wavelength which is very large, you'll never see these small conformational changes. Okay.
That's true.
So why would you want to keep that in the business? When you do these calculations from first principle, you're keeping everything. Right?
Yes,
Like the question that you are trying to address.
That might,
I mean, the experience another thing that is going to address all of these.
no, I think I would tell Shorendu is just he has to first calibrate his method to get to the ionization potential. Just let him do that first. Then he will show that this can be applied to problems where multiple molecules are also involved. So let's first calibrate that.
Yeah, I'm happy to go that way. I'm just asking, is this overkill?
No,
That-
I'll give
We
you
can have a
examples.
discussion afterwards
I
if this is an
guess-
overkill, because let him proceed. Yeah.
So
Yes.
I think I'll give you some examples which will clarify this. So here, just to set the stage and understand what are these one particle levels, right? I've just taken water molecules which has 10 electrons. And now with this particular case, we are talking about fermions. So we could talk about 5 levels where each of which has been occupied by 2 electrons with opposite spins. So if you go about the energetics of these states, they can vary from something like tens of EVs in the valence region, and which can be measured, say, for example, by shining UV. On the other hand, if you want to go to core, you'll have to use a probe of X-ray, right? So, and then you can figure out the core orbital energies. So these are also shown through this simple image here. And here, what I have plotted is the binding energy versus the cross-section. And what you see here are not simple one levels. These are broadened by vibrational features. So in real experiments, there are vibrational effects. I'm not going to talk about them. And these tend to broaden these particular levels, okay? And the other thing, the interesting aspect, for example, if you go from gas phase, core orbital level of water, from gas to liquid phase, there's actually change in energy. I'm going to talk about why this change happens at the very end, in fact, okay? And the other thing, as I promised, is understanding this particular correlation portion, right? So we see, as I said, this will be approximated at random phase approximation. And this particular piece contains 2 parts, the polarization and the dynamical correlation portion, okay? What exactly is polarization? Polarization is actually a simple classical term. So if you were to put, or if you were to fix a point charge, an electron, for example, at a particular point, it is going to induce dipoles which will talk to each other, and they have to talk to each other such that they minimize energy. That would be called the polarization term, okay? So I guess that defines it. The other part, which there is no classical analog, is a dynamical correlation part. So I'm going to call that as a difference between this correlation portion minus the polarization portion, okay? So the way this happens is because you could have 0-point motion of this electron. You could also have 0-point fluctuations of electrons of a water molecules. When these fluctuations couple, that gives rise to a correlation effect, okay? So that is what I'm going to call as a dynamical correlation. And how these 2 factors play out for different molecular systems would be the point of discussion here. Now, just to start things off, again, some simple examples. So I'm calling it one particle energies 101. So if you take a hydrogen atom, right? So the Hamiltonian is quite simple. You just have the kinetic energy and the nuclear electron portion. And then the ionization potential of hydrogen is very well known, 13.61 eV, right? Now, if you go to hydrogen anion, right? So now you have taken the hydrogen atom, added an extra electron. And I asked the question, what is electron affinity for this system? That is, what is energy required to, or gained or lost to add an extra electron to H hydrogen, right? So it turns out if you just look at Hartree-Fock portion, it is unfavorable. No wonder, right? So you're adding an extra electron negatively charged to a neutral system that is going to be unfavorable. However, the correlation portion, it turns out most of it is dynamical correlation. If you were to add that portion, it accounts for about 1.15 eV, and you get an experimental electron affinity, 0.75 eV. So throughout the talk, positive numbers indicate binding, and negative numbers would indicate lack of binding. So here, electron affinity of hydrogen anion is positive. That is, it is favorable to add an electron. And this is coming out because of dynamical correlation effects. A slightly different problem, which I hope I'll teach this at one point. So this is a dipole bond electron. So this was thought about by Fermi and Teller in 1947. So if you take a dipole, right, and add an electron to this, will it bind? Okay. If you take a hydrogen nucleus, right, H plus, and if you take however small nuclear charge, it is going to bind an extra electron. But when it comes to dipole, because of the nature of the potential, there is a positive end, there is a negative end. It turns out there is a critical dipole moment that will only support a bound state. Okay. So here, what are the critical dipole moments that would support a bound state? This was worked out by Fermi and Teller. So it's about 1.63 dBi. If you want all the S-type state, what you have to have is about 1.63 dBi to bind an extra electron. You need 9.63 dBi if you want to have p states and so on and so forth. So this was worked out by Fermi and Teller, and you must be wondering why am I talking about this, right? So one of the interesting molecules, NaCl, sodium chloride, right, part of salt. So if you were to take and prepare this molecule and you prepare the anion of this molecule, it turns out you can actually bind an electron to NaCl. So I have formed NaCl minus, and if you were to plot the density of the extra electron, okay, so this is about 80% density that I have plotted. So if you look at it, it is pinned to the positive end of this NaCl, and it's basically bound because of the dipole moment of NaCl, which is about 9.1 dBi. Okay, so and what is the reason for binding, right? So here, if you were to just use Hartree-Fock, which accounts for electrostatics, the binding is about half NeV, and the remaining portion, the correlation portion, it turns out it is about 0.22 eV. Okay, so this particular anion is called dipole bond anion. These are very squishy in the sense that if you were to perturb these systems, they change a lot. And here the binding energies are, the binding energies of less than 1 eV. So it's 0.72 EV for this NaCl molecule.
So, Vamsee, just a quick question. The bond length of the NaCl typically is not 2.36, is it?
Right.
It's lower. It's actually lower than that.
Yes, it's likely lower than that. This might be the optimized geometry.
Optimized geometry, right? Okay,
NaCl.
of the anion, right?
Of the anion, right? Okay. Now, slightly different states. So here I have xenon clusters. These are not experimentally made. These were just studied theoretically, right? So here, if I take a xenon cluster, there are no permanent moments on a xenon, right? So these are spherical atoms. And if I form a cluster of xenon, if I take about 6 of these, what you would notice 6 atoms and with different configurations. So here I have one linear chain, I have an octahedral framework, and then I have this hexagonal framework. And if you were to compute the binding energies here, right, it turns out the bindings are of the order of 3 MeV. So these are milli-electron volt binding. You will not observe them experimentally. And if you were to plot the density of these states, these densities of this one particle's electronic states, that is, if you were to add an electron and understand where this electron is localized, almost all of it is away from the molecule. Okay, that is what you would see from this picture. And now you could ask the question, what is the reason for binding, right? Now, if you do Hartree-Fock, you get 0, right? So Hartree-Fock cannot support the binding of these states. The only reason they bind is through dynamical correlation, and the binding is about 2 to 9 MeV, all due to fluctuation. So it's all due to dynamical effects that you can see a binding at this particular case. Okay.
Yeah, it's interesting. You went from small molecules to clusters. One jump. So,
right.
I mean, clusters, I mean, how many particles in the cluster?
In general, or
in xenon clusters? For example, it could be 1,000 or no.
This is
right
just,
now it's only 6, you say.
yeah. So starting from about 5, you can start seeing binding.
You can, if you go, then there'll be a lot of delocalization. You don't know where the electron is sitting and so on.
Yes, it could be. Most of the time, these are going to be delocalized. These are going to be delocalized over several
and then there could be collective effects, which Lokesh should go investigate.
Right.
So you're still talking about, when you say single particle state, you're saying that it will be somewhere there. But I can say that's a condition that you can cross. Right? So, I mean, I understand what you're saying, but right now it's still a very small one.
Right. Okay. Yeah. So, I mean, so in principle, you could be studying larger molecules and the same story happens. But roughly, you can say that with increase in size, with increase in polarizability, there will be larger binding energies. Yes.
So I had a question here. It's exactly the point that I was trying to make earlier. You said if you look at the electron density, most of it sits at large distances. That's because it's a MEV binding.
Right.
Okay. So now, if it's sitting at large distances, then and if it's a MEV electron, then it cannot really distinguish much about the core of the electron.
Absolutely.
Of the
yes.
atoms.
Yes.
Okay. So what is the minimum electronic configurations that you need to involve in order to get your calculations right? Let's say to 1%. If you want to get your binding energy, electron affinity right to 1%, okay. What is the kind of electronic, what are the electronic configurations that you need to take into account?
So, so you would consider, say, single slater determinant as a configuration, is it right?
I would say even more. I don't know the levels of the xenon atom. Okay. So n equal to 4 or 5, right? 5.
Okay.
Okay. So the highest one, the n equal to 5, will have 8 electrons.
Okay.
Okay. So can you neglect everything below that and just keep the top 8? Just keep, they're not valence, but they're the topmost. Yeah. Yeah. Outermost shell.
Most of it is coming out from the outermost shell. But see, when you talk about electron correlation, it's also about what kind of virtual levels you're accessing, right? So that the fluctuations are happening because you're accessing virtual levels. Now here, it's what I would say is you can get, say, perhaps 90% of it from, say, the excitation from n to n+1 levels. Okay, these would be like some sort of an S to P type of transitions. So that would be covering up 90%, but then you could also have contribution from, say, you n to n+2 levels. Is it right? So,
okay. I mean, of course, what you're saying is correct because, but as you go to larger differences, energy differences, everything is down by energy.
Right. Absolutely. Yes. Yes.
And the energies, as you go from one n to n prime, okay, the difference goes as 1 by n minus n times squared. Okay. So you need really very few.
Yes, it's very few, but it may still add up very fast, right? As you go to number of systems.
Yeah, so that's the scaling analysis.
Yeah. So
the scaling analysis. As you take the binding energy to zero, as you go to larger and larger clusters, okay, the binding energies will fall. Okay?
Right.
So very large clusters, take, then it will be enough to take one. M and n+1.
Okay. So it's not always true, I think. Just going from n to n+1 may not.
Large clusters.
Right.
So, okay, so we can come back to this question later, but
yeah, we can come back to this question.
Okay. Yeah. Yeah. So now I'm jumping to yet another system. So here it is a water cluster, water hexamer, right? So each water has a dipole. So now I have combined, you can think you have combined several NaCl systems, right? So each water has a dipole, but a single water molecule doesn't have sufficient dipole to bind an extra electron. Now, if I take a water hexamer where the framework is arranged in such a way that it has a sufficiently large dipole moment, and now I compute the binding energies, right? So for this particular water cluster, what you would notice is at Hartree-Fock level, the binding is 0.25. So electrostatics, most of it is electrostatics, contributes about 0.25 eV, whereas the remaining binding energy out of this experimental value of 0.42 eV comes about from correlation portion, okay? And if you were to further split this correlation portion into the polarization, which is like a static effect and the dynamical effect, it turns out most of it is actually coming out from the polarization effect, okay? It's not the dynamical effect that is contributing. So here, the binding energy of 0.42 eV, you can see there is almost an equal split between the electrostatics and the correlation, okay? I'm taking yet another molecular system, same water molecules, right? Now these are arranged in a different fashion. And here, if I were to look at the excess electron that is bound to this water cluster, it is occupying a cavity type of state, okay? And this is much more relevant to real experiments. Now the framework is arranged in such a way that the net dipole felt by this extra electron at the center is 0, okay? So what happens then, if I were to use Hartree-Fock theory here, it turns out the binding energy is 0. Okay, it doesn't bind at all, the Hartree-Fock theory. Same water molecules, right? A different configuration, the binding energy is 0. Now add the correlation portion, the binding energy becomes 0.2 eV, and that is pretty much the exact answer, okay? And it's very, very interesting system here because I can actually now come up with simple models where I only include two body polarization. That is, an electron polarizes a single water molecule at a time. If I do that, the energy, the binding energy becomes 0.43 eV. So it is very important that you account for many body polarization. If you only account for two body, it is over polarizing and over binding. Okay, so this is an interesting system to understand the impact of many body effects versus two body effects. Yeah.
Also, Vamsee, quickly, the transition, you can also calculate the transition energies for the S2P transitions, right?
Yes.
In the valence. So
Yes.
they match up with the experiment to good level? Because some experiments are done on at least solvated electrons.
Yes, they match up to a good level, but
What would be the correct, like, what would be the percentage, like a correction or something that you know of, that how good you can go to the experimental numbers?
see, okay. So what I would say is the experiments, of course, is a convolution of configurational space
Right.
plus the electronic space, right? Now, within the electronic space, we can do very well. So we can go up to 99%. One of the reasons is this is also a simple problem because here you have to just focus on this excess electron. Okay, so if you get those electronic levels of this excess electron, right, you are in business. Okay. So on the other hand, there is a conformation flexibility that really kills this. Okay, so that becomes very hard. Yeah, yeah. All right. Yeah. Right.
Total dipole moment, does it depend only the number or also the way you arrange it?
Yeah, it depends on the number and the way you arrange it, right? And you could actually have configurations which are isoenergetic. So some with very large dipole moment, some with zero dipole moment, they're isoenergetic. So you could have such cases.
Okay.
Okay. Yeah.
Yeah. So the another example is an ammoniated anion. So here I have taken a cluster of 34 ammonia molecules just to show you how the electronic density is if you were to add an electron to this particular system. Okay. So all these systems, water clusters, ammonia clusters, all these fall under the framework of solvated electronic systems. So here you have basically added an electron to the simple solvent molecules, and this is occupying very interesting electronic states. Okay. And where is it exactly relevant, right? So finally, this relevance question. So if you were to actually, if you have done this experiment in your undergrad, for example, if you dissolve sodium metal in liquid ammonia, right, it gives this nice blue color. The reason this blue color appears is because liquid ammonia strips off the outermost electron of sodium and then it dissolves it, right? And then this particular solvated electron, right, which is denoted by this, it actually can undergo optical excitations, which this absorption is happening in red and you see a blue color, right? And very interesting thing happens as you increase the concentration of the metal. So you go from low concentrations to this high concentration. So these are usually denoted by this strange unit, metal percentage mole. So as you go from this value of 0.08 to 9.7, okay, so this is about 9.7 metal percentage mole. So mole percentage metal. What you would notice is the development of a very metallic color. Okay, so this you can do in the lab. And what is exactly happening here is that these solvate electrons, they start to couple with each other and they form an electron gas within liquid ammonia. And this is having the same properties as a metal. So why this transition happens, why it happens at a certain concentration of metal, what are other intermediate states going from this solvated electron species where you have single electrons solvated by ammonia to this electron gas, what is the exact transition, that is not completely understood yet. Okay, so here is a photoelectron spectrum of this system. So here they have, instead of sodium, they have dissolved lithium in ammonia, and they have gone from these low concentrations of metal to very high concentrations. Okay, And as you go and do photoelectron, so you see a single peak at this low concentration, so which denotes the solvated electron system. As you go to higher and higher concentrations, you actually see a development of Fermi edge and a development of a plasmonic peak, which is indicative of a metallic species. Okay, so this is a very interesting system which has been studied forever, but we don't understand the exact dynamics of the changes going from the solvated electron to metallic state.
What is one corresponding?
Yeah, so okay, firstly, these are calibrated with respect to the Fermi edge of this system. And this 1 eV peak corresponds to the photoelectrons which are solvated. So you start from the solvated electron system and you have shine, say, this low energy UV, the electron that you're coming out, those are,
Like lowest bound energy state in the molecule?
no, these are the solvated electrons. Okay, so this was I guess this is what I was talking about so far, right? So these are the electrons. So if I were to add an electron to this water cluster, it gets solvated. So this is the extra electron. It's like a particle in a box in some sense. So you have an extra electron where they're filling the potential of all the other water molecules. Okay, so, right.
That would be the, would you call that ionization potential of this solvated electron, something like that?
See, yeah, exactly. So the way I would call it is like a defect state in this particular liquid. So the defect is caused, the defect itself is an extra electron in this particular case. It's not an additional atom, but it's an extra electron that has been added. Okay. Some people also would like to call it as electron polaron within liquid water or liquid ammonia. Okay. Yeah. So other interesting systems, for example, here, this was a Nature paper just published in 2021. Here, for the first time, they have actually looked at solvated electrons in liquid water. Okay. And what they did here is a very nice experiment. They created this sodium potassium alloy and they made a liquid out of it. And this liquid would come out of a simple nozzle, and then they would evaporate water from ground up, and this water would form a small layer on top of this this metallic drop. And what you can see here is very nice, this metallic state, as well as you could also see this solvated electron, single electron type of state. So this was a very fancy, I would say it's a huge development in terms of understanding solvated electron, because if you were to dissolve sodium metal or lithium metal in liquid water, that's going to immediately explode because of many side reactions, production of hydrogen gas, and so on. However, what they did, they tried to quench these side reactions by actually evaporating just a little bit of water, which would go deposit on this liquid metal, and then they could see the solvated electrons. Okay.
Vamsee,
Yeah.
it's like I can give you 15 more minutes, but
Okay.
that's we have too many questions and interactions. I understand,
Right.
but maybe we can come to it.
Yeah, so maybe I will try to wrap up. Okay, so here, the other thing that, so most of my research actually involves modeling these electronic states, and we face a huge scale problem, right? So we want to make these calculations as fast as possible. So one of the things we realized is that we don't need the complete correlation potential, we just need the polarization potential, and this is much cheaper to compute, okay? So, quickly going ahead, so here is, these are different electron affinities we have computed as a function of size of the cluster. And what we can show is that if you were to include just the polarization potential, which is called the static effective polarization Hamiltonian, SEP, just keep that acronym in mind, you can actually get numbers which match random phase approximation, RPA. And the reason we're excited about this is that this really reduces the computational cost, okay? So the original random phase approximation method had a cost of n⁻⁶. The scaling is n⁻⁶. So if you increase the size of system by twice, the cost increases by 64 times, right? So in 2021, we published a simple algorithm where this cost was reduced by 2 factors of n, right? So the calculations became n⁴ scaling. And now my student Ritaj is working on developing a cheaper version of this particular calculation where we only include the polarization effects. Now, we have to do one single n power 4 step, and this really reduces the computational time. So at the moment, if you want to study 64 water molecules, the computational time is about 10,000 seconds. Okay, so this is what we can do. It's still quite high because if you want to study dynamics, we want to bring this down by further 2 or 3 magnitudes. Okay, and that is going to be a huge challenge unless we start adopting a lot of computers and so on. Okay, so the other thing I want to quickly discuss are electron affinities. What is it?
He's asking why is 10,000 seconds long? Why do you call it long?
Well, so yeah, it's relative to the graduate student lifetime. So
No, but even other computations that happen in other fields,
right.
10,000 looks like.
Yeah, so so I mean, seriously speaking, so it's because you have to actually do this for several configurations. So several configurations. So if I want to understand dynamics, I have to do 1 million steps. So if I want to do a reasonable sampling, I have to do 1 million steps of this. So this is not going to cut it. And yes, I want GPUs.
Yes. And
No, these are all CPUs.
that's right.
Right.
So not my problem.
Please. Oh, that's great. Yeah.
Yes. So all these were CPU based. So there is a lot of scope for improvement. So GPUs can help, right? And they can reduce, they can't change the scaling. They can make it faster. Okay. So I just want to, accuracy is acceptable. So at the moment, the accuracy is of the order of 60 MeV. So that is acceptable because the optical excitations are of the order of 1.5 EV. Yeah, so very quickly going ahead, I want to talk about fullerenes, if that's okay. So it's a very good electron acceptor. If you add an electron to fullerene, it binds about 2.7 EV. Now, these fullerenes have several electron affinity states which are bound. So the lowest one is 2.7 EV, where if you were to plot the density of this excess electron, it is pretty much localized on the atoms of C60. And there are several other states, right? Now, in 2008, there was a very nice experiment where they deposited C60 on a metal surface and they did STM, okay, studies of this. And what you could see is that there are these localized states. So C60, it's pretty much localized, say, if you can, look at my pointer, it's pretty much localized in this region. But when they change the bias voltage, they could see a local density of state, which is spread out much further than the C60, right? And people were wondering what exactly this state was, right? So this particular state is going much beyond the molecular framework. And these states at that point were called superatomic molecular orbitals because these were looking like atomic orbitals, but these were spanning the whole molecule itself. And there was proposal that these particular states, if you have an assembly of C60s, they can have a band structure where the energy versus K dispersion is such that these have an effective mass of single electron. So they can actually pass electrons like a metal. So there was a lot of interest here. So we wanted to understand what this particular state was. So we did calculations very high level at that point, and we figured out that there is this non-valence correlation bound electronic state. So this is purely bound by correlation effects. And if you were to plot the density, most of the density is outside. So we could correlate this superatomic molecular orbital with our calculations. Now, the time to solution for this particular problem on 32 cores is 32 days. Okay, if you want to study this particular state, it takes 32 days. So in 21, the algorithm we developed, it brings down the cost to 5 days. Okay, now this is not it. The experiment they did, they saw other fancy states. They deposited 2 C60 molecules on a metal surface. And at this stage, what they see is hybridization between these SAMO states. Okay, so you could see those hybridizations, and we wanted to understand, what is the basis of such hybridization. Now, as I told you, it already takes 5 days to do that calculation, so it becomes extremely hard. So we developed a little bit of a compression algorithm, right? We wanted to figure out what are the most important orbitals, most important basis functions that contribute to this particular electronic state. Okay, so what Ritesh did was he used the random phase approximation and also the SCP approach. And he saw that SCP would not give you good numbers, but it gives you the right basis. So using SCP, he could compress, he could figure out what were the most important states, and then he could compute the energies, right? So he could, now using the compression algorithm for just the C60, he could bring down the time to 6 hours. Now, further going ahead, we were able to compute this ab initio. So now you could think about hybridization of these electronic states, and this can be done for a C60 dimer. So for C60 dimer experimentally, where these two C60s are deposited on a metal surface, there are several superatomic molecular orbitals. What we could find, which were bound, were only 3 of them, and these were ranging from the energies of 0.28 eV to 0.002 eV, okay? And the time to solution here, now it takes about 2 days with 97% compression, okay? So on a 32 core machine, so we are not using multiple nodes, it's a single node, and it takes about 2 days,
And
okay?
that's the experimental value.
So the experimental values, you can see the bias voltages.
Right.
What I have done is I have shifted them and just tried to compare them. We don't see a good match, okay? So I'm not going into the details. Essentially, you have a metal surface, there could be image effects. So those are probably making the problem harder. So there are a lot of things to do here. So we would, the experimentalists are much ahead. They have also assembled C60 chain here. And as I said, they see nearly free electron bands. We would like to understand such bands, right? So what is the origin of such bands? What is the impact of charge transfer? When you have a metal surface, there could be a small charge transfer that can happen to these C60s. What are the image potential effects? All of these needs to be tackled. Of course, we are also reaching the end of computational power. So what can we do here? We are thinking about this. So these are exciting challenges. And this brings me to the tight part. So what
The time has also become tight. But
So-
anyway, I think this.
so
we can
I'll
just
skip
quickly. Yeah.
I'll skip the intermolecular interactions part, but what I will talk about is very simple thing here. So here I'm looking at the core orbital energies of noble gas atoms. So I have just taken simple noble gas atom, neon, argon, krypton, xenon, radon, okay? And I'm just trying to tell you what are the contributions that form the binding energies, right? So experimental values of these core orbital energies range from 870 eV for neon to 98 keV for radon, right? And if you were to understand, if you want to understand why it is 870 eV, again, you can do this partitioning that I have done. At Hartree-Fock level, it captures most of it, 892 eV. And then the polarization part is actually 23 eV. The dynamical correlation is quite small. Relativistic effects, quite small, 1 eV. SOC is almost non-existent. And the other thing is quantum electrodynamics, right? So even those factors affect the binding energies. So it turns out as you go along this series, right? So while Hartree-Fock is a major fraction, you see that polarization effects increase, the dynamical correlation stays constant. Scalar relativistic effects, they become really large the moment you go up to radon. Spin orbit couplings, despite having 1s electronic state, you can have spin orbit effects that come in. They also become large. And the other part, which is in some sense, in my opinion, is a frontier challenge for this particular problem is thinking about quantum electrodynamics. So whenever you have
Those QED effects exactly zero? Or
no, I have, given the experimental errors, I couldn't really estimate the QED effects. So these are essentially difference between what I calculated and the experiment, okay? They are not exactly zero, they're going to be finite, but the value should be, I think, less than 10th of an EV, that's my guess, okay? So these are numbers some other people have also calculated, the QED effects, and these QED effects can range from 30 to 560 EV, okay? So this is a frontier challenge, can we compute this, right? And what is its impact on actual chemistry itself? We know relativity already, it impacts chemistry. But what about QED, right? Does QED impact chemistry? That is something I don't think we have answered that completely. So some of the efforts in the group are going towards, at the moment, understanding SOC effects. QED is something that we would like to try in the near future. So with that, the 1s shell, yes. Yes, that is true. Right.
These are Accelerator collisions, particle collisions.
Yeah, absolutely. Right. So the thing is, these are an indirect effect, right? So for example,
That also means that the experimental numbers are very uncertain, right?
you're right. Okay. Yeah. So, well, so I guess I got I got to give you a flavor of the research that is happening in a group. So we are trying to understand chemical problems by combining physical theories and computational methods. Most of the time we are making sound approximations and designing algorithms. And the thing I think I wanted to show you, at least one physical aspect, is that the many body polarization correlation effects, they actually vary differently. They are different across chemical space. There are plenty of challenges to work in this field, right? There is need for parallelization, architecture-dependent algorithms. There is need for new theory implementation. We need work in relativistic and QED chemistry. There are a lot of other problems to look at, okay? So there are other projects that are happening in the group. These range from things like modeling X-ray emission, optical spectra of F-centered effects, non-Hermitian quantum mechanics, which is used for understanding understanding resonance states, which actually Vaibhav looks at, and also looking at weak interactions. Okay, and I'll skip this. And then TIFR is a nice place. You can do a lot of collaborations as time passes. So we have had nice, fun collaborations with Vivek's group, mostly on the material side, right? Also looking at excited state dynamics with JD's group. We also collaborate with other theoretical groups, for example, quantum Monte Carlo methods being developed by Andrea Zen. Also looking at charge storage problems with Professor Deepa Kushlani's group. So with that, I would like to thank my group members. It's fantastic to have young, intelligent, and bright students. And most of the work I presented today was from Ritaj and Vivek. I want to thank all my colleagues for creating a very nice environment here, and also, being friendly and also giving a little bit of push here and there. Thank you. And then funding from all the different places.
Okay, thank you. A big round of applause for Vamsee. Okay, so questions from the hall.
In the early discussions you were having, you basically said what you can predict are the electron affinities and ionization energies. And you also later on mentioned dynamics. So you can also predict reaction kinematic, like the speed of a reaction, etc.
Right, right.
Can you also study, for example, how catalysis works with this kind of framework?
So yeah, so catalysis is, you could say it's a special case of dynamics, right? Okay. So here you have reactions where you have a reactant, a surface, for example, which is catalyzing, and then you have products, right? So you can actually do computations for interfaces, so that can be done. So usually in catalysis, what we are interested in is understanding, say, the starting reactant energetics, product energetics, and also the reaction barriers. Okay, so these can be computed through different algorithms. So you can figure out transition states. So that helps you understand catalysis. Okay.
Yeah. I just want to get a sense of, in the Kohn-Sham framework, the kinetic energy functional.
Right.
What is the level of errors that come from the kinetic energy functional? Because primarily the effort is towards exchange correlation, but there is also an effort in terms of the kinetic energy, right?
Yeah, so I would say most of the errors are coming from the exchange correlation part, right? So if you're asking me what is the fraction of kinetic energy that is coming from Kohn-Sham versus the exact kinetic energy, right? I would say there you capture almost about 99% of the kinetic energy. Now this 1% could still be important for chemical reactivity, right? So what I would say is, for when it comes to chemical reactions, right? I would say it is still significant. If you have errors in the Kohn-Sham framework, that would still, I think the errors are as important as the exchange correlation. When it comes to total energies, most of the total energy is captured by the non-interacting kinetic energy. When it comes to differences, there I think the errors can be large. Okay, and other confusing part is what we call as exchange correlation, it actually contains the correlated portion of kinetic energy. Okay, so when we design it, we design to capture even the correlated portion of kinetic energy.
Vamsee, very nice talk. So one question was that when you talked about dynamics and rates of reaction, of course, you can get from thermodynamic quantities in principle.
Right.
I'm guessing that's how you calculate it. So my more question is, can you calculate form factors and can you see how it evolves? Let's say.
Sorry, what factors?
Form factors like correlation functions. You calculated energies.
Right.
Can you also calculate correlation functions
Yes,
or
yes.
form factors?
Yes, you
And
absolutely
for
can.
example, dynamic versions of them, which probably by Voora or someone would have access to in some scattering experiments. That's the kind of question I was asking.
Yes. So for example, we can compute pair densities, right? So you can compute electron-electron pair densities once you have information about wave function. You could also compute pair densities of nuclear positions. So for example, if you do a simulation of water molecules, right? So liquid water, you could figure out, given a fixed position of one oxygen atom, what is the probability of finding another oxygen atom. So this can be done by dynamics. So what you do is you have energy, then you can compute gradients, and then you can put momenta into the system, and then you can do dynamics. So that can be
evolved with that.
Yes.
Okay.
And this could be reactive dynamics and non-reactive. So some of the catalytic aspects, you can run trajectories and do reactions.
Okay. Thank you.
There's a question.
So in most of the calculation, you did Hartree-Fock and you add a polarization term. So within standard DFT, can you add this polarization term?
Yes. So we are mostly working in the density functional framework.
Yes.
So the polarization term, I guess what you mean is, can you add it as a local contribution, right?
So it's like same as whatever you are adding with Hartree-Fock, in some way, is it possible to add within standard DFT?
Yeah, so I think what you mean by standard DFT is local
Yes,
potentials.
local.
So it turns out I don't have a good answer to that. So it's very hard to add a local polarization
So
potential.
even not local, let's say hybrid functional.
Right. So within a hybrid framework, yes, it can be added. Okay. So that is in fact what we are doing, right? So we're going in a hybrid framework, right? So that's why we have this extra term.
So there is no way to locally add those terms.
Maybe one way is to think about some sort of an OEP, optimized effective potential. So that could be a way, but that's going to be not so easy, I think, right? So,
Okay.
yeah.
Yeah, so just wanted to, this is a sort of day-to-day matter. What kind of computation have you accessed so far and what would you need in the future?
So right now, the access that I have are, these are single 20 nodes, okay? And these have completely CPUs, okay? So at the moment, what the algorithms that we develop, they cannot talk to multiple nodes. We can use other algorithms which can talk to multiple nodes. So that is one thing to tackle. But then we will get a speed up of only 20 times, okay? That won't solve our 1 million, sampling
So what do
points.
you want? I mean, if you want to do good state-of-the-art calculation, for example, given
See-
your algorithm and the speed.
So we would like 1,000 GPUs, right? So
No, but I mean, let's not, let's not, I mean, just say, what would it mean in terms of computational power and how much? So do we have access to those or is that too outlandish?
So very few people have access to this in the world, right? So only
And
very
cloud doesn't help you? Everyone is thinking of cloud computing and stuff.
the cloud.
I mean, astronomy, I see lots of colleagues asking for cloud computing help. I don't know anything about computation, but will that help in some way if you can share resources on the cloud or access them on the cloud?
See, I am not completely familiar. See, if you want to use 1,000 GPUs, right? You also want a very nice fast interconnect. Now, for these data farms, I don't think they would provide such specialized systems with, 1,000 GPUs with.
So you have to set it up locally. I mean, I'm just saying that's the way to go.
So I think at least in the country, we should have such systems, at least a few of them, right? So because we are competing with people abroad, so who have access to such systems.
So you
right?
have projected that for the future? Okay.
I have projected part of it. But see, I think there are other things. So to minimum I would, to test my code, I would just need say 4 GPUs, right? But if you really want to have production runs, they should be going across 1,000 GPUs, right? So that, okay, all right, yeah.
Okay, I just have a quick question that, of course, one doesn't expect you have to everything possible to do calculations from milli electron volt to MeV electron volt, small m to capital M. But looking into that sense, the DFT is a very good calculations. For example, molecules like fullerene, C60.
Right.
Now, many times we also study one spectrum, you showed plasmon effect. The
Right.
fullerene's a plasmon effect is very well known, and a lot of people study that. Is it possible from your calculation, because there are two things involved. One is molecule, that part I think you can handle.
Yes,
Other part is a scattering part.
right.
That's either high energy electrons or high energy ions that people use. Is it possible to do such calculations from these kind of molecules? One is fullerene, other one is other carbon-based molecules like PAH, PAH molecules,
Yes,
right?
yes.
Is it possible to do such things here?
So,
Because that will be very, then we have a lot of future.
Yeah, so something like electron scattering we can do. So which is part of this other project that we have submitted, it's under review. Well, it's sort of under review. So these are basically, we're trying to look at electron scattering states. And here what we do is we analytically continue our Hamiltonians to the complex plane. And then we try to figure out where there are stationary points. So we can do that, and we can figure out, these are basically the metastable states of uracil anions. So we can do that. But I think if you're talking about scattering between atoms, I think that might need a slightly different framework. It can be done, I think. Okay. Yeah.
Okay. Last question, Shamalova.
Yeah, it's very interesting. I was just trying to understand that, when you talked about this going from solvated electron to the metallic phase, computationally, can you follow that? How exactly this
Right now we cannot,
happening?
right?
But
So
in
right
principle, it can be done. Eh?
Well, so right now, see, the thing is, we don't even understand the physics of this transition, right? So how do you go from this one electron to this metallic phase? So what is propelling that particular transition? So we don't understand that. So we cannot use a blind theory at the moment, right? So we have to at least go from this one electron to dielectron state. So why would
that is what you have done so far?
That is what we would like to do, I think. Okay. So while in principle, one can do computations, I think we don't have a proper theory at the moment.
Is it possible to go down from the top?
That may be something to think about. Absolutely. So because I think electron gas is something physicists have studied forever, right? So going from there to this other side, maybe that's a good suggestion, I think. Yeah.
Okay. Well, I was trying to extend the discussion section so that I was hoping some people will move out, but we have too many people and less food. So the point here is that we have to share a little bit. But this is fantastic. Thank you for coming in in such large numbers. And I hope, yes. Yeah, and yes, that's a yes. I forget his name. Shoot. Sambit.
So you have only so far used density functional theory. Do you have any other sort of technique in mind that you could have used?
Well, see, so density functional theory, the reason we used was it's very cost effective, computational cost effective. Other theories we have used in the past are things like wave function methods, like equation of motion coupled cluster. So these are theories we have used. Density functional right now is the only way out to study these problems. Okay, so you can go further down, but now you have to develop force fields. Okay, so these will be, you can call them as ab initio inspired force fields. So, but that's very time consuming, right? So the moment you change a system, you have to parameterize again and so on. So this looks like a nice sweet spot to try out.
Okay. Thank you very much, guys. And thank you, Vamsee, for a very engaging colloquium. And and this is just a starting point for the new students. Please do come every week at 4 p.m. Thank you. We walk over to the canteen for some snacks. Thank you.